The way a lens is curved affects how it bends light. See, the light from this candle is going straight into this lens. But because the sides of the lens are curved, the light gets bent. So look, down here we have a blurry patch of light. So I move the screen in. Right here, at this point, that's where the candle flame is in focus. But look, it's upside down. It's all caused by the sides of the lens being curved. Now, if a lens is curved in like this, we say it's concave. Now, concave lenses make things look smaller and farther away, like they're in a cave. Okay? Okay? Ha! Now, if the sides of a lens are curved out like this, we say it's convex. Convex lenses make caves look bigger. Hold on, I messed that up. They make things look bigger. That's right. That's it. The convex lenses, where the sides get bigger, they make things look bigger. That's it. That's what it is. Now, you have convex lenses with you all the time. They're right here in your eyes. Ooh. Anyway, convex, concave. Like a cave, like a...
Like a vex?
Sandy said he could always remember concave by thinking of a sort of a cave, hollow. Convex is the other way.
When we see objects in a mirror, we're looking at light that's bouncing off the object, then bouncing off the mirror, and then coming into our eyes. Here's the thing. Parts of the object that are on the object's right stay on the right. Parts of the object that are on the object's left stay on the left. It's a mirror image, for crying out loud. See, we're facing the reflection, not the object. So that's why we have ecnolibmus. Ecnolibmus.
Hi, I'm Penn, and this is my partner, Teller. We're Penn and Teller. Did you ever, I don't know, look at yourself in a spoon? Well, if you look at yourself this way, you're right side up. But if you look at yourself this way, you flip upside down. Why is that? Well, let's look at the spoon sideways. See, the upside down way, the light waves come in, bounce, and cross themselves, making you look upside down. See? Whoa, 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 whoa.
When light bounces off of a flat mirror, it bounces off at the same angle that it hits. In fact, that's what light does with any mirror. But if the mirror is curved, it's making a slightly different angle with the mirror at different places. So it looks weird. Like, totally weird, man. Like, you could, like, totally, like, freak out. Whoa! See that can? Right there on the bottom. I'm gonna reach for it with this grabber arm of science. But watch what happens. As I aim for the can and squeeze, I miss. Now, I'm really trying to get it. Here's what's going on. The light bouncing off the can is changing directions as it goes through the surface of the water. And so the can looks like it's in a slightly different position than it really is. And I miss. But if I compensate for the refraction of light, I can probably get it. I'm gonna aim a little lower. Got it. You want some?
Here's a light trick that doesn't need mirrors. Put a penny in a pie pan. Now move back so you don't see the penny. Don't move, because I'm gonna pour the water in. It's okay if you make a mess. Pretty cool, eh? See, light's always bouncing off the penny. But when you pour the water in, it makes the light bend. And the bending of the light makes the penny reappear. But the penny didn't move through all of this. But don't take my word for it. Try it.
This magnifying glass is making my eye look big. Now, why is that?
I don't know.
Please consider the following.
Okay.
When light enters something like air, water, glass, or plastic, it slows down a little. And when it slows down, it changes direction. See how one eye is lower than the other? See? Take a look at this. Here are 3 straight beams of light. When they go into the piece of plastic straight, they come out straight. But if the plastic is tilted, the beams of light get tilted. See, they change direction so that they come out this side offset. Now, what would happen if the piece of plastic didn't have straight sides, but had a curved side, like a magnifying glass? Well, the light would change direction, right? Because the surface of the plastic is curved, each beam of light enters the piece of plastic at a slightly different angle, and it changes direction a slightly different amount. Oh, look, over here the beams of light come together at a single point. This is called the focal point. Now, what about the magnifying glass? Well, suppose your eye were over here, and light from the room were bouncing off of your eye and going through the piece of plastic this way. Well, then, the small area at this end would be spread out over a large area on this side. Your eye would be magnified. Ha! Thanks for joining me on Consider the Following.
Clearer than a corner office window. More focused than an automatic camera. Able to read fine print with a single glance. It's Lindo Lens. Disguised as mild-mannered bank teller, Stephanie astigmatism, Linda uses a variety of concave lenses to bend light entering her eyes whenever things get blurry. Lindo Lens, defender of sight, focus, and the 20/20 way. Today's episode, Hocus Pocus.
Try this. Get a glass of water and a pencil. Stick one end of the pencil below the surface of the water. And look, the other end disappears. You can only see the end of the pencil that's underwater. That's because the light is bouncing off the bottom surface of the water. It's what we call internal reflection. It's reflection inside. The same thing happens in this plastic rod. I'll shine the small laser in one end. Watch. Most of the laser light stays in the rod and doesn't come out till it gets to the other end, see? Pretty cool. Anyway, this is called an optical fiber. And that's how modern telephone calls and computer information are sent all over the world. The telephone call or the computer information is changed into a beam of light, sent down an optical fiber, and then decoded at the other end. Oh, excuse me. Hello?
Billy boy?
Oh, it's my mom. You guys go ahead. I'll catch up with it.